All right, let's start. Uh, Last time we have an introduction lecture on HPC, which is high performance concrete. Today, we're going to discuss SCC, which is one type of HPC. It is called self-consolidating concrete. Okay. So first of all, why we need to consolidate the concrete? I think everybody know that already. There's several purposes. One is to get rid of large voids, especially honeycombing. We need to fully compact the concrete. The concrete need to fill every corner of the formwork, and also to ensure there's good bonding between the concrete and the rebar inside. Okay. We can use rodding or vibration rod to consolidate the concrete. Okay. But too much vibration and consolidation, we may have segregation or bleeding problems. Okay. Too less consolidation, we may have honeycombing. Okay. That will reduce the strength and also the durability of concrete. So that's the reason we need to fully compact the concrete. Okay. So SCC is a special type of concrete, does not really require any type of consolidation. Okay. So concrete that flow like liquid without segregation and bleeding and need no external consolidation, both during and after placing. Okay. Conventional concrete, we need to test the slump. Okay, as how many inch the concrete slumped after we leave the slump cone. Okay. And for SCC, we measure the diameter of the concrete pie after the concrete stopped flowing under its own weight. Okay. So I think we mentioned about this when we talk about fresh property of concrete. Timeline of SCC, the first idea, first prototype of SCC is from Japan, Professor Ozawa in 1988. Okay. And the first field application of SCC also from Japan 2 years later. Okay. So in the North America, in the US, it's around 2000 spread SCC to the United States. And 2 years later, in 2002, we had the first North American conference in Evanston, Illinois, which is near Northwestern University. Okay. In 2002, I just began my PhD study on this type of concrete, and I attended that meeting. This is 19 years ago, almost 20 years ago. And I have been working on SCC since 2002. Until now, we also have a research project try to bring SCC to the state of Hawaii, mainly because our special morphology, a special shape of our local aggregate make it very hard to design the SCC using our local aggregate. So the main focus on SCC is fresh properties. There's 3 fresh property requirement. The first one is called flowing ability. The second one is called passing ability. And the third one is called segregation resistance. Okay. Flow ability is easy to understand. We need to measure the slump flow for the concrete to achieve at least, I will say, 24 inch. And the segregation resistance means the coarse aggregate should not settle to the bottom of the concrete. Okay. For passing ability, that means the coarse aggregate need to be carried out by the cement paste and not lag behind when the concrete is flowing. Okay. Here is the video showing us how SCC is flowing in the formwork. As we can see, the rebar is highly congested. Okay. Let me see if I can play this video. Sorry. Okay. All right. Okay. We have some other video to show you in a moment. Hopefully they work. Okay. So we need a lot of chemical admixtures such as superplasticizer and VMA, which is viscosity modifying admixtures to increase the viscosity and yield stress of the concrete to make sure the three fresh property requirements are met. And also we need higher cement paste content to ensure these three requirements. And also we need better gradation and smaller aggregate to help achieve these fresh property requirements. Pros and cons of SCC. The advantage of SCC including reduced total construction cost. Okay. The material cost will be higher, around 5 to 10%, okay, higher than normal concrete, but because the labor cost is hugely reduced, so the total construction cost will be lower. Okay. It will also speed up the construction process, okay, because normally the consolidation take a lot of manpower and hours in the field. So using SCC, we can speed up the construction process. And also noise reduction, because we do not need to vibrate the concrete using the vibrator. And also because the concrete can easily flow through restricted places without segregation. We have more homogeneous concrete, no honeycombing, no large air voids. So that can enhance the strength and enhance the finish on the surface of concrete. The drawback of SCC including lack of globally agreed testing method for the fresh properties, and also we don't have a well-accepted mixed design method for SCC. And again, the material cost will be around 10% higher compared to conventional concrete. Right. SCC is widely regarded as one of the greatest advances in concrete industry over the past 2 decades. Okay, so this is one of the buildings. Is the Central in Cincinnati. This is cast by self-consolidating concrete. All right. 10 years ago, 2011, we have 9.1 magnitude earthquake in Japan. So this is March 11th, 2011. Okay. And at one time, there's a nuclear reactor. It's called Fukushima reactor. It's in danger of leakage of the nuclear materials. So people are thinking of entomb everything using SCC, because SCC, you can cast the concrete very fast, and you can also pump the concrete over longer distance, so you can reduce the radiation dangerous to the water. So SCC can be pumped at, this is 220 cubic yard per hour from a long distance, 230 feet pumping distance. Okay, so luckily we do not really need that. Okay, but this is one of the options. They ship this 70-meter, 190,000 pounds of pumping trunk moved from the US to Japan just in case to entomb everything using SCC. So that is 10 years ago. So summary of the fresh property test and the controlling factor for the fresh properties. For flowability, a controlling factor including the volume of the cement paste, the viscosity and yield stress. So we call that rheology of cement paste. And also the gradation and the packing density of aggregate. And then we use the slump flow test. Sorry, it's not slump test. We call that slump flow test to quantify the flowability. For passing ability, we need to control the maximum size of the coarse aggregate. So smaller the coarse aggregate, the potential for blockage behind the rebar will be less. And also we can reduce the volume of aggregate and improve the gradation of the aggregate, so that will improve the passing ability. We'll talk about airbox test and also the gearing test in a moment. This is for passing ability. For segregation resistance, the controlling factor including the water-cement ratio. The lower the water-cement ratio, the lower the potential for segregation, of course, because the viscosity of cement paste will be higher. More sand can also improve the segregation resistance, and VMA can enhance the viscosity of the cement paste and greatly reduce the potential for segregation. And we'll talk about HPCII and column segregation tests for segregation resistance of SCC. So the slump flow test, we mentioned that already. We use the same slump cone, but normally we put the smaller opening at the bottom. Okay, so we lift up the concrete will flow under its own weight, and we measure the time for the concrete to achieve 20 centimeter, 20 inch or 50 centimeter in diameter. Okay, so we call that T50 time. So that's the measurement of the viscosity of the concrete. And we also measure the diameter of the concrete after it stopped flowing. Normally, it should be more than 600 millimeter, around 24 inch. We can also see if the concrete segregates by look at the perimeter of the concrete. Sometimes we see a layer of cement paste beyond the coarse aggregate, which means at the very edge of the concrete, we do not have any coarse aggregate. So that's the indication of segregation. So we can see a potential segregation by look at the perimeter of the concrete, but that sometimes is not very reliable. So this is the video for the slump test. Hopefully the video is working this time. All right, so fill the concrete with one lift. So no need for 3 layers. Lift up, record the concrete flow diameter to achieve 20 inch and measure the final diameter of the concrete pipe. Okay. So that's the slump test. The L-box test, which is shows in the picture here, so it's indicator of the flow ability and passing ability. So the L-box has a vertical leg like this, and also a horizontal leg. Okay. And there's a gate between the vertical and horizontal legs, and behind the gate there's a rebar. Okay, there's 3 rebars behind the gate. So what we need to do is we fill the we close the gate first, and we fill the concrete in the vertical leg. Then we lift the gate, so the concrete will flow to the other end of the horizontal leg. And we measure the height. H1 is the height at the beginning, and H2 is height at the other end of the horizontal leg. And we also measure the time for the concrete to flow. Okay. So this is a pretty empirical test for flow and passing ability of SCC. So this is the video. Close the gate, fill the concrete. You see the rebar here? We have 3 rebars. Lift the gate, count the time, reach the other end. Okay. So if the concrete has good passing and flow ability, H1 and H2 will be similar. Okay. This is from another view. Okay. So J-ring test is another test for passing ability. Okay. This is a combination of a ring, and you can see we have rebars at around 3 or 4 inch in space. Okay. This is outside the slam cone. So what we do is we do the same slam cone test, but just with the ring. Okay. So if the concrete has some potential passing ability problems, then the diameter will be smaller compared with the slam flow test. Okay. So by compare the diameter with the ring and without the ring, we could have an idea of the passing ability. Okay. So this is the so-called J-ring test. This is a test for segregation. We call that column segregation test. In the size of the column is around, say, 10 inch and diameter and around 26 inch in height. Okay. There's a top, middle, and bottom sections. So we fill the concrete from bottom to top and let the concrete to settle. Okay. So if that's a segregation, then in the bottom section, we should have more coarse aggregate than the top sections. So after the concrete settle for around 10-15 minutes, so we take both the top and the bottom section, and then we wash the concrete over a number 4C using water. So we weigh how much coarse aggregate left on the top and the bottom, and depending on the difference of coarse aggregate of the top and bottom sections, we could have an idea of the potential segregation problems. Okay. But this time need a lot of water, a lot of concrete, and also a lot of labor. It is not very suitable in the field, in the job site. Okay. This is the standard test, ESTM standard test. So here's one example of study the dosage of superplasticizer affecting so S35F means flash, I believe. So 35 means 0.35 water to cement ratio. Okay. Just an example here shows if we increase the percentage of flash, we can reduce the amount of superplasticizer needed to achieve the same slump. So that means we can reduce the cost because superplasticizer is expensive and flash is cheaper compared with cement. Okay. So again, just an example to study the flow ability of SCC. Okay. So this is the, I think, the same test, but for the strengths. Okay. So measure 1 day, 7 day, and 28 days. So the blue is 1 day. Okay. The red is 7 day. And the 28 days is the yellow. Okay. So what we can see is for early age up to 28 days, if we increase the percentage of flash, okay, so the strength will be lower. So that makes sense because post-magnetic reaction is slower. So right. So that's true for both 0.35 and 0.45 water cement ratio. Here is the same concrete, but show the permeability. Okay. What we can see here is we have 2 weeks permeability, which is blue. Red is 16 weeks. What we can see here is we increase percentage of flash. The 16 weeks permeability will be much lower. Okay, much lower compared with 0% of flash. Okay, so we can see the benefits of flash occurs at later age, after several months. Okay, in the first month, first 28 days, we do not really see much benefits in the strength and sometimes permeability. Next, we're going to talk about testing and modeling segregation of SCC. This is part of our work here at UH. We did between 2011 to around 2015. So here talk about the problem of SCC, especially segregation. Okay? Because we use a lot of superplasticizer, okay? So the flowability is very high, but because the viscosity is low, the concrete is very easy to have segregation problems. Okay. As we can see here, the coarse algae settle to the bottom, and on the top layer, we don't have any coarse algae. Okay. Segregation can occur after the concrete is casted in place, okay, when concrete is not flowing. In that case, we call it static segregation. And segregation can also occur when concrete is flowing, because one of the major advantages of SCC is we do not need any vibration. So many times we let the concrete to flow, we just pump the concrete at one location and it will flow to the other end of the formwork, maybe 30, 50 feet or even more. So this is one type of, one example of so-called dynamic segregation. Okay. When the concrete flow over a longer distance, it will lose some of its coarse algae. Okay. In this example, at the end of 50 feet, concrete lost all of its coarse algae. As you can see from the coarse here, no coarse algae at all. Okay. So again, there are two types of segregation. Static segregation means the settlement of the coarse algae in a vertical direction when the concrete is not flowing or static. So static segregation will cause concrete to crack because only cement paste will shrink. Okay. So on top of the concrete, we only have cement paste, so the shrinkage will be higher. So we may see cracking in the top surface of concrete. And also non-uniform strengths, okay, due to segregation and also bleeding of concrete, and the lower surface abrasive strengths. Right. Dynamic segregation means separation of the coarse algae and the cement paste when the concrete is actually flowing. Okay. So this picture is the strong wall to simulate the earthquake of some structure members, like the column here. The strong wall is casted in University of Illinois using SCC, I think around 2006 or 2005. Okay. So in that concrete, we see a lot of dynamic segregation, loss coarse algae gradually over the flowing distance. Okay. In the big picture, we can see we have less and less coarse algae when we increase the flowing distance. So this is the pump location. This is the cores we drill at different distance. So we also did some simulation trying to study how this segregation can affect cracking. We simulate using the finite element method, study the stress, tensile stress inside the concrete. If the concrete has segregation, the tensile stress will be higher because, again, shrinkage is only occurs on cement paste. If the paste percentage change at different location, so we have some internal tensile stress developed. We also try to develop more testing method because the currently available method is not very field friendly. It's labor consuming, material consuming, and also need a lot of water. So we're trying to develop some of the method, new method, which is easier. So we can use that in the field. Okay. And also we're trying to understand the mechanism of segregation. So better understand the mechanism, we can better control the problem. Okay. So we did some of the tests, some new tests for segregation, some new tests for both static segregation and dynamic segregation. And we also simulate, do some modeling work for static segregation and the dynamic segregation. Okay. So I will just give a couple of examples on the new tests we developed for static segregation and the modeling work for dynamic segregation. Right. So this is called image analysis method. We use a free software called ImageJ. Okay. We're trying to take the picture of the cross section of the concrete, okay. And then we using some algorithm. Before we do that, we change the color picture to a binary picture, okay. And then we use algorithms such as erosion and hole filling to get rid of the sand particles, okay, because we don't really care about the sand. And also we fill the small holes in some of the coarse algae, like you can see from here. Okay. So if you compare this large particle on the left and the right, we can see that particle on the right has no white holes. Okay. So that's called the hole filling. So that's the dam is done automatically using the software. So after the treatment, we can count the areas of the coarse algae at different levels, so we can better quantify segregation. Right. We also developed a new testing method. It's called the segregation probe. So the probe is made by a steel wire. I think the diameter of the steel wire is 1/16 of inch. Okay. So we designed a probe so it can penetrate the layer of mortar on top of the concrete, but it cannot penetrate coarse algae. Okay. So we design the mass, the weight, and the geometry of the probe so it can only penetrate a suspension with a yield stress less than 30 Pascal. Okay. Because for normal paste and mortar, the yield stress is less than 30 Pascal, around 6 to 15 Pascal. So it can penetrate the paste and mortar, but cannot penetrate concrete because concrete has more than 50 Pascal for the yield stress. Okay, so that's the design. The idea of design is probe. Okay. And based on the penetration depth, because the probe can measure the thickness of the layer. Okay, so the penetration depth is the layer, the thickness of the mortar layer on top of the concrete. So we can give a so-called stability reading from 0 stable, 0 and 1 stable to 2 and 3 unstable. Yeah, this is how the probe is just settled by itself under its own weight and stop on the top of the coarse air weight. All right. And again, we do some modeling work to simulate the stress at different stability level from 0 to 1 stable. That means the stress level is not high enough to crack the concrete. 2 and 3, the concrete may crack due to severe segregation. We also, based on that method, we developed a so-called hardened visual stability index, or HPCII. The test is very simple. We cast a concrete cylinder, 6 by 12 inch cylinder, and we cut it in half after it hardens. And by observe the distribution of coarse aggregate over the cross section, similarly, we give a rating of stability. Okay. So right now it is the AASHTO standard testing method. This is one of the national standard method for SCC. So next, I'm going to talk about an example of modeling dynamic segregation of SCC. Okay. And these slides talk about the difference between the two types of segregation. Okay. For static segregation, it is settlement of coarse aggregate when the concrete is not flowing. But for dynamic segregation, because it occurs when concrete is flowing, so factors such as the flowing velocity of the concrete, how fast you pump the concrete, the drying force of the flowing, okay, such as the hydraulic pressure or the pumping pressure, and even the friction provided by the flowing surface will affect the segregation process. Okay. We simulate the flowing process of the concrete based on another new testing method we developed. So this is for dynamic segregation. Okay. So we pour the concrete in this little trough. The trough has around 7-degree angles. So the concrete will flow from the higher end to the lower end. Okay. And we take samples before the concrete flow and after the concrete flow. And we compare how much coarse aggregate loss at these two samples. Okay. So we study the forces acting on the aggregate and also acting on the cement paste, and we try to simulate how much segregation it occurs during this flowing process in the flow trough. Okay. Here just show the forces acting on the aggregate. Okay. So let's just look at here is the forces acting on the aggregate. For aggregate, they have the frictional force, the TA, which is acting on the aggregate by the surface of the trough. Okay. Another force is called FA, which is the drag force. Drag force is acting on aggregate by the cement paste. So if there's a tendency for segregation, then we have a drag force, which is provided by the cement paste on aggregate. GA is the gravitational force because of the 7-degree slope. Okay. And here shows the equations governing the three forces, TA, FA, and GA. I think delta rho is the density difference between the cement paste and aggregate. Phi is the volume fraction of aggregate. Also, we have viscosity of cement paste. Delta V is the velocity difference between the aggregate and cement paste. R is the size, the diameter of different aggregate. Tau 0 is the yield stress of cement paste. Okay. MA is the mass. Okay. So that's the force on aggregate. And the bottom shows the force acting on the cement paste. Okay. Similarly, we have three forces, as you can read from there. So they are a function of the paste viscosity. Okay. Vp is, I believe, is the velocity of the cement paste. Tau is the viscosity. Okay. I think A, B, and C are geometry of the flow trough. Okay. So we get the equation for the forces acting on aggregate and acting on the paste. Okay. So based on the forces, we can calculate the A, which is the acceleration on aggregate and cement paste. Okay. And then we can do integration using Mathematica or MATLAB. Okay. So we can calculate the velocity. So VA is the velocity for the aggregate. VP is the velocity of the paste. Okay. And then we can further integrate velocity into S. S is the how much distance the aggregate traveled. Okay. And how much distance cement paste traveled. Okay. If there's difference on how much distance aggregate and cement paste traveled, then that will indicate we have a segregation problems. Okay. So from the force, we do calculation and we can calculate a curve of DSI, which is the dynamic segregation index from the flow chart. Okay. As we can see from here, this is the travel distance in meters. This is the segregation. Okay. Right. So that's the modeling work. And we also try to compare the modeling work with some of the experimental work. Okay. So we use some real aggregate, and we also use some of marbles, because for marbles, it is perfectly spherical shape. The size is fixed. Okay. So it's easier to compare with modeling work. We also measure the velocity, viscosity and yield stress of the cement paste, because that's the parameters in the equation for the forces, like here. Okay. So basically, we use aggregate and we measure the viscosity of the cement paste, and the yield stress of cement paste. Okay. So we try to compare the modeling work and the experimental work. Okay, like here, so this is a field testing result. That's the real work. And the red line is the simulation work from the software Mathematica. Okay. So basically, we see okay agreement between the simulation and the field testing method. But because the field result, field concrete, we use the real angular shape aggregate. That's one of the reasons we believe for the difference between the simulation and the model work. Okay. Right. Here, study the effect of the size of aggregate, okay? Both from the simulation work. So this is the line is the simulation work. So the red line is simulation of segregation for 15 millimeter marble. Okay. The black line is simulation work for smaller 10 millimeter diameter marble. Okay. And the dot, we only have one dot, that is the segregation at 6 feet or around 1.8 meter. So we measure that using the flow trough. So we see pretty good agreement for simulation and experimental work. And both simulation and experimental work showed us if we can reduce the size of L gate, we can greatly reduce the segregation. Okay. And here just show the reason for smaller segregation for smaller L gate is because we have a higher drag force if we reduce the size of L gate. So higher drag force will reduce the potential for segregation. And similarly, we studied the effect of gradation of L gate, both simulated work and field result, not field result, lab result show us better gradation, we can reduce the potential for segregation. That is because, again, better gradation means higher surface area. That means we have higher drag force to reduce the potential for segregation. Change volume of L gate does not have a much effect on segregation. As we can see from here, we vary the percentage of cross L gate volume by 10%, but we see not a big difference in segregation. The density of L gate play a bigger role. Okay. We compare two different type of L gate with 2540 and 2580. So not a big difference in density, but we see a big difference in segregation. Okay. So here again give a explanation based on our understanding of the mechanism. So higher drag force, higher forward acceleration provided by FA for lower density marbles. Okay. So again, by doing the simulation work and verified by laboratory result, we have a better understanding how segregation is affected by different parameters, so we can better design concrete with good performance. So this is effects of paste rheology. Okay. So we use different viscosity. So this is the 0.02 Pascal second for plastic viscosity. So yield stress, 0.01 Pascal. Another one has a higher viscosity and yield stress. And we see a huge difference in segregation. Okay. So higher viscosity, higher yield stress will greatly reduce the segregation. But at the same time, the flowability may be lower. So how to balance the flowability and segregation is the major task for successful SCC. This is effect of initial velocity of the concrete, how fast you pump the concrete. It doesn't see big difference for the pumping speed. Doesn't see a big difference in segregation when we change the pumping speed. All right, so this is the summary of the study by us around 5-6 years ago. Some new testing methods for segregation, both statically and dynamically, and we do some modeling work to better understand the segregation problems. Okay. So based on this study, we try to optimize SCC using our local Hawaii aggregate. As I mentioned, our local aggregate is very porous. The absorption capacity is much higher compared to aggregate from other layer. Okay. So we try to optimize the mix and also minimize the cost. Okay. Improve the workability, trying to reduce the shrinkage creep and improve the durability. Okay. So here is the old slides I believe I showed when we talk about airgate properties. So just the three functions of cement paste. Okay. So we need some paste to just cover the surface of airgate. Then we need more paste to fill the interparticle space, as we see in these blue colors. And then we need more cement paste to increase the distance, so the coarse airgate will not touch each other, so we have a higher slump. Okay. Right. So this is how one case study we trying to optimize the mixed design of SCC using our local airgate. Okay. I think this is done by one of our undergraduate students. Okay. I believe I remember his name is called Akira Ito. He calculated optimized airgate proportion for any given local fine and coarse airgate. For example, Halawa 3F, Kappa chips, and Emerald 3As. Okay, and he can calculate the packing density. Okay. So this is how we choose the airgate proportions based on modeling of packing density. Okay, so this is we have three different type of airgate, sand, and two type of coarse. Okay, so we figure out at what combination of coarse and fine we can find the highest packing density, so we can better optimize the mix proportion. Okay. And here shows some other modeling work for viscosity of concrete, okay, and yield stress of concrete. Okay. This is viscosity of cement paste. This is the volume fraction of airgate. And this is the maximum packing density of airgate. And that is intrinsic viscosity of airgate, which is depending on the shape, morphology of airgate. Okay. So we can, based on these models, we can predict the viscosity and yield stress of concrete based on airgate properties and the rheology of cement paste. Okay. So before optimization, we see the concrete. This is the so-called SCC we borrowed using mixed design from other place. Okay. As we can see, the concrete is very stiff. It's not very flowable. After optimization, the concrete is very flowable, and at the same time, the segregation probe cannot penetrate the concrete, which means the segregation resistance is very good. Okay. All right, I think that's the end of today's lecture. So I gave introduction of SCC, the history of SCC, and what we have done about this special type of concrete. Okay. All right.